Okay, so over the last two videos, we've explored the idea of rate of change, constant rates of change, average rates of change, instantaneous rates of change, etc., etc. As I mentioned in the previous video, what we're aiming towards with the process of differentiation, which is what we're looking at in this topic, in the first calculus topic, is we're aiming for a technique that will enable us to calculate the gradient of a curve at any point. That's what we're aiming towards. And we are getting closer to that goal. Before we can actually get into that process, the next two lessons are going to be around looking at limits. Okay, so again, these are tools or techniques that we need to have an understanding of so that we can then calculate or learn how to differentiate. Okay. So again, a bit standalone for now until we can put things together in a couple of videos' time. So you might recall back in our exponentials unit, we started the unit looking at an example which involved a kangaroo attempting to hop across a 400-metre wide paddock by jumping half of the remaining distance with each hop. Okay, and we established at the time that the distance in metres after n hops was given by this particular rule. So 400, we're multiplying it by half, we're halving it every time he hops. So that's times half to the power of n, so times half to the power of the number of hops. We could write that then as that's the same as 400 on 2 to the power of n, or it's 400 times 2 to the power of negative n. And we use this as an example where we see exponential decay, essentially, that reflection in the y-axis, which means that the remaining distance is decreasing with each hop. But also we talked about it as an example of the fact that it also suggests that the kangaroo will technically never have zero distance remaining. Now, while practically that's not true, if the kangaroo didn't have any size and was an infinitesimally small point, then that point would never ever reach the other side of the paddock. Okay, so at the time, yeah, as I said, we talked about the fact that he would have to make infinitely many hops if he ever wanted to get, you know, well, he would still never actually technically make it to the other side. But the point is that as he hops more and more, the remaining distance is getting closer and closer to zero. Okay, and we can write that mathematically using the idea of a limit. Okay, so this would be the equivalent statement here. The limit as n approaches infinity. So as he takes more and more jumps, as n gets bigger and bigger and bigger and bigger, the limit of this calculation will be zero. Okay, so as n gets bigger and bigger and bigger and bigger, this whole calculation here will approach zero. So the limit is equal to zero. The limiting value is zero. Okay, so we don't say that the limit approaches zero. The limit is the value that the function's approaching, okay, and the limit is equal to zero. So our notation, and in fact I'm going to develop a habit where we start to always write this in brackets too, because I think people make poor use of that limit notation. I think brackets might help us. So we're calculating, and technically they probably should be there as well, because otherwise, well, is it the limit just of 400, or is it actually the limit of all of this? Okay, so the limit as x approaches a of f of x is equal to L, is what we've got written here in this box. Okay, so as x gets closer and closer and closer to the value a for this particular function, the limit of that is L. Okay, the function approaches a value of L, so the limiting value is L. Okay, so in many cases, limits can be evaluated by simple substitution. So the example I've used here, substitution, is a bit more complicated, although we can think it through, because while we can't technically substitute infinity into something, we can understand that when I raise a fraction to a very, very big power, I get a very, very small number. And a very, very small number times 400 is a very, very small number. Okay, so we can think through the logic of that. When we might be limiting to a particular numerical value, quite often the limit is simply about substitution. Okay, we'll have a look at examples where it's not. So if I want to know the limit the limit of 2x minus 8 as x approaches 3, we simply want to look at, well, if we can work out what 2x minus 8 equals when x equals 3, then the limit is going to be that particular value. So if you think about, I'm just going to draw a graph here so 2x minus 8's a linear function. So let's say that's our function there, 2x minus 8, that's 4, that's negative 8. Okay, so what we're saying is as x approaches 3, okay, so as we're travelling along this curve, so that's the point 3 there, okay, and we can calculate the value of 3. When x is 3, y is going to be 6 minus 8, so it's going to be 3 negative 2, okay. So what we're saying here, as x gets closer and closer to 3, so as I'm travelling along this curve with the x coordinate getting closer and closer to 3, whether I'm coming from this direction or from this direction, what value of the function am I actually approaching? And I'm approaching a value of, sorry, it's not 3, it's negative 2. So as x approaches 3, as my x value gets closer to 3, my y value gets closer to negative 2. And it can, in this case, it can actually equal negative 2. So the limiting value can actually be a value that the function can get to, or it might be an asymptote, for example, like we saw in the hopping mad example. Okay, the function can't actually be equal to 0, but the limit of the function as x approaches infinity can be 0. Okay, in this case, the function can be equal to 3, and so therefore the limit as x approaches 3 is simply that value. Okay, so we just substitute 3 in. So this is, so now that I'm able to calculate the limit, once I'm able to substitute 3 in, then I can lose the limit notation, because what I'm now doing is calculating that the limit is 2 times 3 minus 8, which is 6 minus 8, which is negative 2. Okay, so just want to be careful about that limit notation. One thing that people often do wrong is they write the limit as x approaches 3 equals. Okay, again, this is an operation. It has to be a limit of something being equal to something. Okay. All right, part B, again, we can evaluate that when x equals negative 2, and so therefore the limit of this quadratic function as x approaches negative 2 will simply be the value of the quadratic when x equals negative 2. So it's going to be 4 minus negative 2 squared, so it's 4 minus 4, so it is 0. Okay, so if we think about this graph, it's a sad parabola, plus minus 2. Okay, so as x approaches negative 2, so as we head towards that point on the graph, the y value is clearly approaching 0. Okay, now this one here we potentially, oh no, we don't, sorry, I thought it was a different example. Okay, so again, we can evaluate this when x is equal to 3. So we're going to do that. We're just going to simply substitute 3 in. So if you can evaluate the limit through direct substitution, that's all you need to do. Okay, so as x approaches 3, the limit of this function will be what we get when we sub 3 into this function. Okay, so that's going to be 7 on the numerator over square root of 12 minus 6, so square root of 6. 7 on root 6, you can rationalise if you want 7 root 6 on 6, but both are perfectly valid and correct. Okay, now sometimes we're not going to be able to just simply substitute the value in, and that's where we might get an indeterminate or an undefined limit. Okay, or sorry, we don't get an indeterminate one, but just substitution can lead to an indeterminate or undefined expression. So expressions where we end up dividing by 0 are undefined. Okay, they can't be evaluated. However, sometimes we might get expressions where we end up with, if we substitute a value in, we end up with 0 divided by 0, and that's indeterminate. Okay, it may or may not be defined, and we might be able to, before we do the substitution, manipulate the expression to an extent where we don't actually end up with 0 over 0 when we substitute in. Okay, so for example, if we were to think about this particular function here, and we were to calculate the limit as x approaches 1, okay, so that would mean, first of all, seeing if we could substitute 1 into that expression. So when we work out f of 1, sub x equals 1 into the expression, we get 1 minus 1 over 1 minus 1, and we get 0 over 0, which is indeterminate, which doesn't necessarily mean that the limit doesn't exist, but it does mean that f of 1 cannot be calculated. Okay. So, however, it's still possible to determine the limit. So if we have a look at what happens as x gets closer and closer and closer to 1, I've just constructed a table of values here to help us see that. So we can see, if x is 0.9, we can't actually calculate it. When x equals 1, we can't actually calculate the value of this expression, but we can calculate it for values close. When x equals 0.9, the value of the expression is 1.9. F of x is 1.9. F of 0.99 is 1.99. F of 0.999. So as x gets closer to 1, f of x appears to be getting closer to 2. The same thing happens as we approach 1 from above. So if we look at when x equals 1.1, when it's 1.01, 1.001, so we're getting closer and closer to the value of 1, we can see that the value of the expression is also from both sides getting closer to the value of 2. And so even though we can't actually evaluate f of -1, we can still determine that the limit as x approaches -1 of this expression is equal to 2. Okay, now we don't want to have to do that by, table of values and subbing in lots of points, but what we want to be able to see here is that actually if we had simplified this expression algebraically before we made the substitution, we could have calculated this. So the limit of this expression, we know we can't just sub 1 into that. It gives an indeterminate expression. So let's think about the fact that, and I'm going to put brackets here, and I'm going to put brackets here, as I said before. So again, I haven't calculated the limit yet. So this is still equal to the limit as x approaches 1 of, and all I've done is rewrite this x minus 1. We know x squared minus 1, is the same as x minus 1 times x plus 1. What that allows us to do is simplify this expression. Sorry, that won't cancel. This one. Dividing by x minus 1. So what this is actually the same as is calculating the limit as x approaches 1. And again, I still haven't actually calculated the limit. I haven't substituted x equals 1 in yet. So it's still equal to the limit as x approaches 1. So you can't lose that notation. Okay. The limit of this is equal to the limit of this, which is equal to the limit of this. Now I can sub x equals 1 in. It's equal to 1 plus 1. Okay, so please be careful about when you lose that limit notation and where it goes. Okay, so the limit as x approaches 1 of x plus 1, I can now sub 1 into that without creating an undefined or indeterminate expression, and so the limit is going to be equal to 1 plus 1, which is 2. So we can calculate it algebraically. If you were to draw a graph of x squared minus 1 over x minus 1, it's actually the line y equals x plus 1, which is what this simplified to, okay, with a hole in it. Let me show you on the CAS. If I graph x squared minus 1 over x minus 1, x minus 1. Okay, it looks like a line, but if I were to graph trace, menu 5, 1, okay, let me see if it'll scroll to 1. Okay, jumped over 1. But when I'm in graph trace mode, I can jump to any point on my graph just by typing the x coordinate. So if I type 1, it brings up x equals 1, and when I press enter, it'll jump to the point where x equals 1 on my graph. And actually when you do that, it says that it's undefined. So there's essentially just a hole in the graph at that point. Okay, and so that's why we can't actually evaluate f of x when x equals 1. Okay, it doesn't exist at that point. But we can calculate the limit because we can see that as we approach 1, so as we travel along this graph getting closer and closer to an x coordinate of 1, we are clearly getting closer to a y value, or the function being equal to 2. Okay. Alright, so when substitution produces an indeterminate result, we must look to see if some algebraic manipulation will enable us to evaluate the limit using substitution. So, for example, in this particular question here, let's work out the following limits. So if I were to sub x equals 2 in here, we won't get a 0 denominator, that's no problem, and we won't get, but we'll get a 0 numerator. But it's a 0 denominator that's the issue, and the fact that we won't get a 0 denominator means we can directly just make this substitution. Okay, so this one is, we sub in 2 minus 2 over 2 squared plus 1. So that is 0 over 5. That's not indeterminate or undefined. 0 divided by 5 is 0. The limit is 0. Okay. Alright, part B. Limit as x approaches 3. Now, if I were to substitute x equals 3 into here, the denominator would be 0. Okay. So if I were to do this, we're going to get 2 times 3 plus 1 over 4 times 3 minus 12. So that is 5 plus 1, so 6 on 0. Now this is an indeterminate because it's not 0 on 0, it's 6 on 0. 6 on 0 is undefined. So this limit is undefined. Okay. Part C, if we were to sub 4 into this, we get 4 squared minus 16 over 4 minus 4. So we get 0 over 0. Which is indeterminate. Okay, so instead we want to think about if we can manipulate this, and we can in this case. So this is equal to the limit as x approaches 4 of, that's a difference of 2 squares, x minus 4 times x plus 4 over x minus 4. The x minus 4s are going to cancel out. So I'm simply calculating the limit as x approaches 4 of x plus 4. Now I can substitute x equals 4 into that without creating an indeterminate expression. So I can get 4 plus 4, which is 8. So the limit is 8. Alright, part D. If I were to sub x equals 2 into here, I would get 2 minus 2 over, that's 4 minus 10 plus 6. So that's 0 minus 0. So again, that's indeterminate. So let's see if I can actually simplify this first. So the limit as x approaches 2. Right, so rule number 1 of trying to simplify an algebraic fraction is factorise everything, so you can see whether there's any common factors that will cancel. The denominator will factorise as x minus 2, x minus 3, and so therefore we can simplify this expression as 1 on x minus 3. And now we can substitute 2 into that without creating an indeterminate expression. So now that we're substituting in, we're taking the limit, we can lose the limit notation. So it's the limit of 1 over 2 minus 3, which is 1 over negative 1. And so it is, the limit is equal to negative 1. So if you were to draw this graph, as you travel along the graph approaching the point with an x coordinate of 2, the value of the function is getting closer and closer and closer to being equal to negative 1. Or the y coordinate is closer to negative 1. It's possible for the limit not to exist, okay, and we've seen that happen in part B. It's an undefined limit in part B. We can't manipulate it. It's not an undefined limit in part A here. The limit is 0, but part B we have an undefined limit. So it's possible for it not to exist, and we'll have a look at that further in the next section. So if you want to evaluate a limit using your CAS, so let's perhaps look at example C as an example. So you're going to get the limit template. So template palette is next to the number 9. Press that. The limit template is down here in the bottom row. Pressing that. I want to calculate the limit as x approaches 4. Oh, sorry, not A, 4. I'm going to leave that little power box that's greyed out blank. We don't need to put anything in there. I'm going to put the expression that I'm calculating the limit of. So it was x squared minus 16 over x minus 4. And we indeed get 8, which is what we found. Okay, so the work today is from a worksheet that's available to you on Canvas, and the worksheet is all about limits. So I want you to practice evaluating them by hand rather than using your CAS, but just some familiarity that your CAS can also work them out for you.